So I thought I'd finish some research off on some geostatistics for when we have complicated domains that we want to model. We want to build models for grids and then warp these grids and then build our statistical model on this warped grid and stuff. And I thought, right, I'll finish that work off and talk about that. So I started making some slides on that. I was going to talk about that, and then I thought the other day there might be a way in which we can do some other thing in a fairly simple way. So I abandoned all that, and then I'm just going to talk about this end thing at the end. And so what we want to do in work package 2 is downscale some climate data that goes into JULES to roughly parcel level so that we can run JULES at roughly parcel level. And we have settled on using the UKCP18 data, which is 12 kilometer, downscaling this with Jonathan and Ilya's mesoclim code, which we can choose for any kind of resolution we want, as Ilya was showing yesterday. Now, the issue with the UKCP18 data is this is 12 kilometer data for daily maximum temperatures for days in July 2070. July is in inverted commas because UKCP18 seems to think years have 360 days and there are 12 30-day months in a year. But anyway, so this is their 7th month, and we get this kind of 12 kilometer data out of it. But UKCP18 at 12 kilometers only gives us data for RCP 8.5. We want to project temperatures into the future, drive JULES with these temperatures, and it's therefore I think irresponsible of us to just be saying we think everything's going to follow RCP 8.5 in the future. What we can also get from UKCP18 is 60 kilometer data for RCP 8.5, but also for RCP 2.6. And so therefore it is 2 RCPs is better than 1. So this is sort of giving us a bit of spread in what might happen in the future. But now we're only at 60 kilometers. If we want to do something at parcel level and downscale with the mesoclim package, I think we'd be a bit uncomfortable taking something at 60 kilometers and trying to end up at parcel level with it. So what we want to do is to think, can we use this to kind of build a new UKCP18 at 12 kilometer data and then downscale this within the mesoclim package? So what we can do is we can build a statistical model that just mimics what the 12 kilometer data do. And this involves a few assumptions. So Ibis was talking about this yesterday. We can build statistical models that will let us represent these processes. And the kind of models Ibis was talking about yesterday let us represent these processes at any kind of resolution we want. And then we can say we want to work at things at 12 kilometers. And then what we want to do is to think about, well, can we somehow link our 12 kilometers and our 60 kilometer models so we can get something sensible at 12 kilometers coming out? And we can kind of simplify our statistical approach by just building a kind of empirical model and then assuming everything is a multivariate Gaussian. And this is a bit like if you have a sample of data, you want to fit a normal distribution to it, all you need to do is to calculate the sample mean and the sample variance, and then you can have your best estimate of a normal distribution. And you can do exactly the same in multiple dimensions if you want your best estimate of a multivariate Gaussian distribution. So this isn't really a model provided apart from the assumption that you think everything is normal. And we can kind of go back to this one a bit later, because lots of climate variables are not very normal. Right, so this is a simulation from our statistical model, which hopefully looks fairly similar to what we started off with, allowing for different day-to-day variability and so forth. Now, what we want to do is to say we want our simulations to meet a certain criterion. On this, what we're going to have on this occasion is we're going to say we want to simulate from our model such that each day the average temperature across our domain is 20 degrees Celsius. Why do we want to do that? Well, if we've got our 60 kilometer data, we can use that as giving our averages, and then say we want our 12 kilometer averages to match up with the averages as what's coming out of the 60 kilometer data. So that should hopefully give us trends over time that are consistent with the 60 kilometer data, but actually giving us data representing 12 kilometers. So here we simulate 8 days of data saying we want the average across our domain to be 20 degrees Celsius. So what we can do, we can say, well, actually we want the average to be, the averages coming out of our 60 kilometer data. This is for RCP 8.5 and this is for RCP 2.6. So we're simulating at 12 kilometers, but getting data representing different RCPs. So this is how we can kind of build a new UKCP18 for a different RCP. Right. When I was talking to someone about RCPs, they said I was very old-fashioned. So we don't do RCPs anymore. We do SSPs, socio something pathways. Michael, no, there you go.
Shared socioeconomic.
There you go. Shared socioeconomic pathways, and what's that for? Oh right. So if we do this for every day in our 60-kilometer data, we can simulate forward and look at the mean difference between our RCP 8.5 UKCP 12-kilometer simulations and our 2.6 thing. And our mean difference looks like this, going from 1 degrees roughly over the sea to 3 over the land, over the hilly bits of land at least. And we can then go back to our 60-kilometer data and say, what does that difference look like in the 60-kilometer data? And it looked like this. So we're getting something consistent with the differences that we started off with in the 60-kilometer data. So our model is at least doing what we want. Whether the 60-kilometer data is doing what we want that to do is a different matter, but we can think about this one a little bit later. Right. So RCPs are apparently very old-fashioned. We don't want to do this kind of thing. And we've only got 2 of them at least anyway from this 60-kilometer data. So if we go to CMIP6 and we go to CMIP6's scenario MIP, loads and loads of models there, loads and loads of scenarios, and loads of variables, all the variables we need to go into JULES. So here are our average temperatures for this region I was looking at in the southwest, based on 4 different SSPs. Each has 3 ensemble members. So what we want to do is think, can we use this data somehow in our simulations that are hoping to mimic what's happening in the 12-kilometer UKCP18 data? And so this is our mean temperatures for our ensemble members in this Access CM, I think it might be CSM2 model, I'm not quite sure what it's called, in the CMIP6 thing. This is the same variable averaged over our UKCP18 12-kilometer data for RCP 8.5, which is 1 RCP as opposed to the other one before, which was 4 SSPs, but 12 ensemble members. But I suppose you might expect less spread given that you've just got 1 RCP as opposed to the other one, which was 4 SSPs. But anyway, the stuff is sort of consistent, so this is at least going on the same path. This is kind of reassuring in some sense. So what we can do is we can simulate from our 12-kilometer model, say we want the mean to look like the mean coming out of our CMIP6 simulations, and then take the mean of our simulations from our model, and then the means look like this, which is matching up with what we started off with roughly, which is quite encouraging in that we're producing simulations based on conditional on different SSPs that we've seen coming out of the CMIP6 data, and hopefully this is going to help us drive JULES in a more representative way into the future. Right, that's temperatures, which we can model reasonably well as being Gaussian. Precipitation, not so much. So here we have precipitation coming out of these CMIP6 averaged. This is month 1, so January. Also, CMIP6 thinks a year is 365 days, so we can condition on the days in that and actually get simulations going out into normal years, which is kind of useful. Different months. The thing to note here is that the mean precipitation doesn't seem to be, this is just for the southwest, doesn't seem to be varying too much across these SSPs, at least not in a really separate way that we saw with the temperatures. it's possible that maybe mean precipitation isn't what we want to look at. We might want to look at days above a certain level of rainfall or something like that. We might see clearer things. But nonetheless, we still might want to think about, do we want to be trying to build different SSPs into our precipitation simulations that we're going to put through JULES into the future? And we therefore need to deal with something like this. So this is the distribution of precipitation, daily precipitation for one location. I think this location is somewhere near Exeter. I don't know why, but everyone just picks that one. So it's the part of the grid cell in the southwest nearest Exeter. And one of the things, we can't model this as Gaussian, but we could attempt at least to say, well, we think the end bit of it looks like a Gaussian, and then anything less than a certain value, we're just going to say is 0 or something like that. But we can model it this way. We get something like this, which is not a good model. But if it was a good model, we could still simulate from this in the same kind of way and get precipitation simulations, average them over our time periods, and then they're matching it with what we started off with before. So provided we could get a good model for this kind of thing here, we can still do the same kind of thing. So wind speeds, another thing we're going to want to put into joules. Here we have average wind speeds for month 10, October. I chose October because in a former life I was doing statistical modelling of wind gusts for reinsurance people, and they said October's the bad month because the trees have still got leaves on and stuff, and then they blow over, damage our buildings and stuff, and we have to pay loads of things out. But when they've dropped all their leaves and things, they don't really blow over quite so much. So I picked October here for that one. Here we have our daily wind speeds coming out of something. And we can simulate from our model. Oh, I've lost some of my slides. Right, here we have our distribution of wind speeds. If we try and fit a Gaussian distribution to it, it's not great, and we're going to get some negative wind speeds for a start, so this is not a good thing. People's favourite distribution for wind speeds tends to be the Weibull distribution, which is a slightly better fit. It's not great. We can think about this a bit later. But essentially what we can do is we can take any distribution we want. Once we've fitted a distribution, we can take our data for any distribution we want to it. If we've got a good fit, we should end up with something that has a uniform distribution that we can convert through our estimate. And then if we know that something has a uniform distribution, we can convert it again, so we think it has a Gaussian distribution. And then we're back on the case where we have things being Gaussian. So what we want to do is then to think, well, we want to simulate our wind speed so that the mean wind speed is consistent with the mean wind speed of some kind of lower resolution model, so the mean wind speed is coming out of CMIP6. Here are our original mean wind speeds that we want to match with our simulations. Here are our things when we model, try and convert things to being Gaussian. So we can model this kind of pattern between the two. So we want to take our mean wind speeds, convert them to these kind of values, condition on these in our simulations, and then we can simulate things through in this kind of way. So we're simulating wind speeds at 12 kilometers such that the mean of each day matches the mean coming out of the CMIP6 simulations. And so we can then aggregate these simulations again over our different SSPs, and we get wind speeds going forward for different SSPs at 12 kilometer resolution. And when we've got all these things at 12 kilometer resolution, we can feed them straight into the mesoclim model and downscale and get everything to go into joules at parcel level. So the things seem to simulate things and they match up fairly well. Need to do a bit of work on precipitation to get this to do something sensible. So far, I've mainly just been looking at building a model for 1 month. So temperatures have this cyclic pattern in a year. We can very easily just build models for each month and stick them together. But then we're going to get sort of discontinuities at each month. And I don't quite know how a tree responds well to discontinuities in the data going into the JULES model. So we have to think about that, smoothing things out a bit. We also really want to make sure our day-to-day consistency is good. So our stimulated wind speeds on one day the sort of correlation between those and a previous day is sensible given what we get in the data. But some of that does come out on the fact that we're conditioning on some data that has consistency across the different days. Yeah, that was mainly all I wanted to say on this. I had to rush these slides together a bit, so it's mainly plots and stuff, but no maths in there. Right, thank you.